Okay, so this is the official beginning. We are very happy to have this exciting discussion between a leading molecular biologist and bioinformatic, Michael Levin, and also a very fine theoretical biologist, William Miller, with a very vast publications on cellular information. And then, please, Michael, if you want to start the session.
Sure. Yep. Let me share the screen. And okay, here we go. And okay, thank you so much for having me here, for organizing this. This is really fun. I'm looking forward to discussing. What I can say, first of all, is that I run a wet lab, and we do experimental biology, but as well as some computational work. And in these 20 minutes, what I don't have time to do is to show you the primary data, which we have quite a bit of, and maybe in the questions we can talk about it. So what I thought I would take my 20 minutes to do is to just tell you what I think is the kind of conceptual landscape that I see here. And if you want to look at all of the things that have come from these kind of views, which have been many specific applications in birth defects, in regeneration, and cancer suppression, in synthetic bioengineering, and so on, you can see all of those at our website. And there are many long talks showing all the data. And then this is my personal blog about what these things mean. But here let's just talk about what I think is the conceptual landscape. So what I want to talk about is the impasse between the mechanistic kind of worldview and the approach of organicists. So roughly speaking, the mechanistic worldview goes like this: we know what matter is. We also know what life and mind is, and in particular, the things that we think about as being interesting in terms of living things and cognitive things are reducible to physics or maybe to chemistry. Machines are certainly reducible to physics or chemistry, and that there are sharp categories. Things are either living or they're machines, but in the end, they all kind of reduce down to the laws of physics and chemistry. So that roughly, and I'm painting with a very broad brush here. Everything I say, of course, there are many subtle views in the community, but I'm kind of giving you the big picture. Now, so this is kind of the reductionist mechanist worldview. Now, there is an alternative, and the alternative goes like this. We agree that we know what matter is. We are working on what life and mind is. We agree that things either are living or they are a machine. And we will give you the fact that we will give you this idea that machines are reducible to physics. But the one thing that we're going to argue as organicists is that life and mind are not reducible to physics. Now, there's something interesting going on here, which is that this, in many ways, is a kind of appeasement strategy, in that they agree on many things. You know, they agree that something actually is one or the other, that it's binary. They even go so far as to agree that fine, machines are reducible to physics and to algorithms and things like that. They're going to keep this. This is the one thing that they will sort of argue about. But they do concede this point. And what I'm going to argue about here is that this is a mistake. That actually organicists should take their ideas even more seriously than they do, and that for the same reason that they do not concede this point, they actually should go all the way and not even agree to this. This is the problem. And I think I think there's a few reasons why they don't do this. First of all, binary categories make life more simple. It's easier if we can believe that we are sort of cutting nature into discrete categories. There's also, I think, this kind of scarcity mentality, in that if we include in our club of special important moral agents, that is, things that we should care about, things with real minds, whose welfare we need to take seriously, that there may not be enough compassion to go around. That it's dangerous to attribute these qualities to too far outside of the club of living things, or maybe even just mammals or so on. It's dangerous because eventually we will run out of care and compassion. And actually, what I found is that the organicist response to my ideas, which I will show you momentarily, has been actually way more negative than the reductionists. because this idea that actually they need to take these ideas even more seriously is disturbing, and it's disruptive, and it actually this community actually finds it much even harder to swallow. So here's what I'm going to say. That we really should take these ideas way more seriously, because if once you go down this road, this type of concession basically just slides slowly but surely. It slides towards eliminativist views, where people where inevitably people will try to go into this position. I think that we have to reject binaries. I think this does not do us any good whatsoever. I think all of the important things here are a continuum. And most importantly, I think we have to keep in mind that nothing is any of our formal models. Nothing is a machine. Nothing is a pathway, or any of these other metaphors that we come up with. All we can do is come up with perspectives on different systems, and an experiment, not ancient philosophical categories, is the way to determine which of those perspectives is optimal for any given system. And I think we have to take very seriously that empirical success, not explaining past things that have happened, but actually how generative a certain view is towards the future. In other words, does it enable new discoveries and new capabilities? Is a good guide to whether we're on the right track, but not just because we're going to engineer widgets or do biomedicine or anything like that. It needs to do that, and it needs to be able to guide a new ethics that are appropriate for where the science is going. And so the things that I'm going to claim today are these. These are my main claims. First of all, that cognition goes all the way down. Okay, life is what we call a set of stories or models that align competent parts towards a larger scale whole. In other words, living things are systems that are very good at aligning their active components towards a larger scale set of goals in some new problem space. I think the magic here is not the material. It's a kind of causal architecture that I will mention briefly, and it's a process of multi-scale sense making. I think that things that are high on that spectrum that I'm talking about are things that are consistently and continuously trying to make sense of themselves and their world around them, and bind their parts in a way that make them aligned towards that story. I think that most current machines, and let's say computer architectures, don't actually do this, but they could. I don't think there's anything special in here about evolution. I think that the natural trial and error has no monopoly on making these kinds of minds. And I think to the extent that we understand how it works, we can do this in many different materials. I think cognition is fundamental. I think it is a superset of life. I don't believe there is really any quote unquote dead matter or passive matter. I think there are minimally cognitive systems that look like matter to lazy observers. And most of all, I think we need really fundamental humility, because we tend to think we know what machines do. We think we know what algorithms do. And I think that for the exact same reason, we don't expect the rules of biochemistry to encompass the story of the mind. We have to now understand that algorithms and materials do not tell the story of even simple machines. So this is the idea of the view that I'm proposing here sees more mind around us, not less. And my goal is to try to take the organicist views to their logical conclusion. So this is the sort of thing that many people start with, which is this ancient piece of art called Adam Names the Animals in the Garden of Eden. And what's happening here is that you have a set of discrete forms, okay, and they're different from this one, and it gives the idea that we know what these are. They're all kind of natural kinds. And in particular, one interesting thing about this image is that it was in this story, in this ancient biblical story, it was up to Adam to name the animals. God couldn't do it. The angels couldn't do it. It had to be Adam. And I think this has a profound lesson for us, because we are going to have to name, in the ancient sense of discovering the true nature of something. When you give it a name, you've discovered its true nature. We are going to have to name a wide range of beings with whom we are going to live, because this idea that a modern human, an adult modern human, is some sort of a sharp category that features in all of our philosophical discourse on philosophy of mind and so on. there really is no such sharp category because, of course, we are at the center of a smooth continuum. Slowly and gradually, we start life as a single cell, both on our own organismal scale and on the evolutionary scale. We slowly and gradually become this sort of thing. Okay, and we have this lovely agential glow that we can all agree we have. And then there are many questions about where and how it shows up. There are no sharp transitions here. And now we know that both through biological changes and technological changes, there's another continuum where there's going to be there's going to be a whole spectrum of all kinds of beings where it's going to be extremely difficult to say what exactly it is according to any ancient categories. So what I think we need to do is what happened with the electromagnetic spectrum. Before we had a proper theory of electromagnetism, what we had, first of all, were lots of different phenomena, static electricity, lightning, waving magnets around, and so on, that were all thought to be distinct phenomena, and there were massive areas of the spectrum of which we were completely ignorant. We just had no idea it was there because our natural ability to detect is all focused in this tiny little area of wavelengths. But what the unifying theory of electromagnetism did for us was, first of all, allow us to understand that these various phenomena were actually all just forms of one underlying thing. And the other thing they did is to allow us to develop technology to detect that thing in all sorts of unfamiliar guises. So we could finally detect X-rays and gamma rays and radio waves and all of this stuff. So this is what I think we need to do. The field of diverse intelligence is really aimed at understanding what is the foundational spectrum across which all systems lie. What is it that scales up as you move across it, and how do we use it to detect minds all around us that are really difficult in our kind of evolved firmware, really difficult for us to notice. This is the sort of thing I'm interested in doing. Of course, developing frameworks that allow us to understand and ethically relate to all sorts of weird things, not just the familiar kinds of animals, but actually new forms of life, different types of active agents. I'm not the first person, obviously, to try for this. This is Rosenbluth, Wiener, and Bigelow back in 1943 tried to make a spectrum so that we could understand what is the scaling here. And I think it's very important that when we look at spectra like this, we understand that we are not really arguing about what anything is. I don't believe there is any way of saying what anything actually is. What we are arguing about for any given system is what bag of tools, what interface, what approaches are going to be optimal for interacting with that system. In other words, hardware rewiring, cybernetics and control theory, behavior science, psychoanalysis, and love and friendship, right? Different ways of interacting with systems. This is not just about engineering. I mean, back here it is, but by the time you get here, it's a mutually vulnerable way to interact with each other. And so this is all about figuring out where systems fit on the spectrum, which cannot be done from a philosophical armchair. You have to do experiments. And we've done this again and again in our lab by not assuming where things are, but actually testing the various tools that are applicable to these different categories. We find cognition in really unfamiliar places. And so we need to figure out where things stand. This is what we are all made of. This is a single cell. It's an organism called the lacrimaria, one cell, no brain, no nervous system, very competent at its own local tiny little goals. It's got a small cognitive light cone, but does very well managing its physiological and metabolic states. It is actually full of this stuff. If you wonder how come this thing is so competent, well, it's full of this. So the little, you can see, if you were to zoom in, you can see little gears and little rods and all kinds of things. This is the mechanism that is underneath all of this. And it turns out, as we discovered recently, that even the material inside of that cell, never mind the cell itself, but even just the molecular networks inside are capable of 6 different kinds of learning, including Pavlovian conditioning. And we're taking advantage of that by training these pathways. And we have applications such as drug conditioning, where you train these pathways to specific stimuli and so on. So what we're talking about is not only are we a collective intelligence made of many parts, but actually the cells and the molecular networks inside are also a collective intelligence. This kind of capability propagates all the way down. And what life does very differently than current machines, okay, is this allegiance to saliency of information, not to its fidelity. So basically, and again, I don't have time to really go into this unless somebody asks later, but both on an evolutionary timescale and on your own behavioral timescale, because you don't have access to the past, all you have access to is the information engrams that were left for you by past versions of you. So your memory traces in your body and your mind, or the genetics that have been handed down to you. At any given moment, your job is to actively recreate the meaning of that information and deploy it adaptively into the future. So this part, the early part of that bow tie, is algorithmic, because you can compress past experiences into a very thin representation, kind of the middle node of this bow tie or autoencoder architecture. But then this part is creative. What you have to do as a living system is to say, what do my memories actually mean, and how do I reinflate them, because they were compressed. You have to reinflate them into the current context. And so the process, for example, of embryonic development is not a hardwired rollout of instructions from the egg. That's not what it is at all. This is a creative problem-solving process that takes this information as basically prompts or cues, and then interprets them. And again, we have lots of examples in biology that show how this process is active and creative. And so, because biology assumes that the hardware is unreliable, okay, unlike our current computer technology that has separation of layers and redundancy and error correcting codes, all designed to keep the data exactly as they are, biology has no hope for that. You know that on every time scale you will be mutated. You have no idea how many copies of any protein you have. All of this is very unreliable. The sense making, the requirement to cobble together the best story you can every single however many 100 milliseconds or 200 milliseconds that you can to use this information to drive into the future. It's a highly creative reconstruction. It is not a mechanical deduction, and it is not a reliance on the like an overtraining on the meaning of that prior data. You are free to in fact, you have to reinterpret it. So this is what's going on in the biological architecture. That is not how we do computers today, but we could. But also, it's really important. I mean, this is amazing, and this gives rise to. By the way, all of this is described in this paper. This gives rise to many remarkable aspects of life and cognition. It kickstarts the intelligence ratchet very early in evolution, because the more creative and you are at problem solving at this level, the less selection can actually see the genome, because the mapping becomes incredibly complex and it hides information. And so then evolution ends up doing a lot of work on this process here instead of on the structure. But we really need to keep this in mind. This is not something that we can easily detect, and something that only happens in advanced, life forms, because even extremely simple things. So you can take a look at this paper on classic sorting algorithms. So these are the sorting algorithms as people have studied for many decades, like bubble sort and things like this. 6 or 7 lines of code, fully deterministic, no hidden mechanisms like you have in biology, very simple stuff. And we found that if you look at them in a particular way, you discover new competencies. Yes, they sort numbers, but while they're doing it, they do some interesting side quests, is the only way I can describe it, where they do other things that are actually not in the algorithm at all. And they have other competencies like delayed gratification and so on. So my point is, and we have a lot of things coming on this kind of trajectory, showing very simple things having emergent, not just complexity, not just unpredictability, but emergent goals and competencies that are not at all obvious from the algorithm. And so it doesn't take cells or life or huge complexity to have these kinds of things. We need to be very, very careful with this, because if even bubble sort has unexpected competencies, then we have to be very minimal in what we say about language models and AIs and whatever. You know, this thing where people say, "Well, I know what it does. I make these things. It's just linear algebra." We didn't even know what bubble sort really does. So we have to be very careful. And so I think, you know, Magritte's famous painting, "This is not a pipe," reminds us, and I had our graphic designer draw me this. This is not a Turing machine. None of the things that we deal with are our formal models of them. When we say that algorithms can't do this or that because there are certain limitations, or machines can't do this or that, those are limitations of our formal models of them, but they are not. We cannot confuse them for the actual thing. Okay, and so for the exact same reason that that these kind of formalisms fail for life, and why we know that the rules of biochemistry are not enough to understand the mind. For the exact same reason, our thinking about algorithms and materials should not be taken to demarcate what it is that quote unquote machines are doing. And the bottom line is, and I could talk about this if people want, the reason I think this is true, and this is what I think the Garden of Eden actually looks like. It's a remarkably wide set of active agents, and you can read more about this here. What I actually think is going on, both for quote unquote machines and for what we think of as living organisms, are that they are not driven fundamentally by, certainly constrained by the physics of the world, but they are fundamentally driven by patterns in the Platonic space. These are patterns, not just the kind of stuff that mathematics studies, so low agency facts about prime numbers and things, but actually high agency patterns that we would recognize as kinds of minds. And these things, it can ingress into the physical world in a wide range of constructs. Some of them evolved, some of them designed, and some of them hybrid. And I've spoken to all kinds of people in the Buddhist tradition, in Vedanta, at the Vatican, rabbis, lots of different people who, in theory, actually are all about the kind of the ineffable and the sort of animating spirit. But they all seem extremely sure that that whatever this is, the ineffable is only going to come through into biological forms. And I've yet to have anybody tell me why exactly that would be. And I think that's basically very short-sighted. And I think that all kinds of constructs can take advantage of what it is that makes life and mind special. And for this reason, much like what happened with mathematics, where we started with simple natural numbers, and then we sort of enlarged what we understood is possible. Sometimes it was very disruptive. This guy Hippasus went and drowned himself at sea because they discovered a new kind of numbers that were very disturbing to them. And we need to do this for ourselves, and hopefully not be as disturbed, because we understood the cognition in brainy animals, and then eventually other life forms. And I'm saying basically not just all biologicals, but a much wider set of agents. And it gets much wider, which I don't have time to kind of talk about here. So I'm just going to stop here and just say just say a few things. We're dealing with an agential material, and the way to understand what's going on here is through pragmatism, pluralism, and a field that Josh Bongard and I call polycomputing, which focuses on the perspective from which different agents see each other. I think intelligence is ubiquitous, and we have a lot of mind blindness in the sense that we are very bad as humans at recognizing it in unfamiliar embodiments. It operates in many problem spaces that are hard for us to see, and we really need to understand this better. I don't believe we make intelligence, either in the biological case or the engineering case. I think what we make as physical objects are pointers or interfaces that facilitate ingressions of specific patterns. And the research program is to study the contents of that space, as mathematicians do for a corner of it, and to understand the mapping between those pointers and the things that come down when you create those. And it's critical because because of the creative problem solving capacity of these agents, almost any combination of living material and engineered material and software is some kind of possible being. There are already cyborgs and hybrids and various other kind of creatures walking around, because all of us have inputs from this space of patterns. And the natural world is here, but we are all going to be living in a much broader world, which it is critical that we begin to recognize these other minds around us so that we can have more ethical interactions with them. So I'll stop here and thank you. And Jeremy Gay drew all the illustrations for today. So thank you. I'll take questions.
Okay, many thanks, Michael. Let's go ahead with Will Miller, please. William Miller. Your talk, Bill.
You're muted, Bill.
You should open your microphone.
Okay. You can hear me now, and you can see my screen. Hello? Oh, okay, good. Michael, that was a tour de force. I loved it. And I think you know from our previous discussions that you and I really share substantial agreements about the living frame. There's no question that there's a continuum of diverse intelligences. I think we have yet to explore all of the interfaces. But my point of contention would be that in the end, there is a distinct separation between the living frame and the abiotic realm. These are differences that make a difference. They're all based on the specific qualities of information in the living frame. And so I'm going to defend my point of view from placing it into a framework which is relatively unfamiliar to most biologists, and that's concentrating on the particular characteristics of cells, and beyond all else, the primary characteristic of the living frame, that all biological information is ambiguous. And from that, I will explain why I believe that there is a binary. It may not be as hard as fast as we had understood before, that there is a binary, that I agree with you, Mike, that we create meanings, intelligences create meanings, and the living state has a particular set of competencies that we have no idea how to imbue into the abiotic realm. So if we take the living cell, the proposition that all biological information is ambiguous is really not theoretical. You simply have to examine the explicit circumstance of every cell. If there's an environmental stimulus, there's a cue. In order for that stimulus, the effect of that stimulus to reach the cell, it has to traverse a medium, sometimes a complex medium, and there's a necessary time delay. That passage means that there is going to be some obligatory degradation of the quality of that environmental cue before it reaches the cell. When it reaches the cell, it's going to encounter an outer envelope, its plasma membrane. This is not just an inert packaging. This is a highly complex, discriminating, intense part of the cell. It's multi-layer. The transit is going to be noisy. When it reaches the cellular interior, it's a crowded, active environment with multiple agential materials within it, all of which are additional sources of noise. So that we're left with a circumstance that every cell has to contend with. All biological information is ambiguous. And it's actually that ambiguity that propels the internal state. It's the foundation of self-reference. The reason that cells have to measure their information is because it's ambiguous. And if it weren't imperfect, they would never expend resources in order to go ahead and assess their value. And so perfect information would never require measurement. So we know that the cell is stuck in that living context. But there's an extremely important codicil that arises from that. It means that since the cell is measuring its information internally, from which it will derive informational meaning, it is actually creating its information. It is self-generating all the information that it has about the external environment. There's no way it can get any access to a pure environmental cue. And that is the concept of info-autopoiesis, which is originated by Jaime Cardenas Garcia. He's on our call here. And I think it's a vastly underappreciated aspect of the living frame. From that internal representation, that process of self-generation, we get the self-referential internal representation of external reality. There's nothing in computers, nothing that we have on the horizon about computers that would actually match that specific living process. And we are in the circumstance then where the basic living information processing unit, which is the total competence cell, there may be competences within sub-agents within the cell, but the cell acts as a competency unit, and it is exclusive, self-referential, it is individually problem-solving and decision-making, and it is creating its own meaning. And we can illustrate this, perhaps oversimplistically. Biological information and computer data bear no actual relationship to one another. Computer data is a square wave. Obviously, the diagram is a little bit oversimplified, but the principle is correct. In the living frame, it's a sloppy, noisy, analog signal. These are fundamentally different information profiles. And from that, we get the foundation of self-referential awareness, the internal state. Every single individual cell is an aware, self-referential observer participant. And there are multiple characteristics of self-referential information that get too little emphasis as far as I'm concerned. One of them is antipodal information, the subjective appreciation of information by two different observers. That's Tosi and Peter's work back in 2008. The idea is simple. Most of you already know this. You toss a soccer ball in the air, you have two observers on either side. They're going to see different facets of it. They're going to be en face to different aspects of that stimulus. It's the same stimulus, but it's different to them. Of extremely important aspect of self-referential information is Pedro's and Jorge Navarro's concept of distinctions on the adjacent. If you have an uncertainty gap, it's extremely important for a living agent to narrow the bandwidth of that gap, the distance between the adjacents. And this gives us a deep understanding to the particularity of the living frame. It's the narrowing of the doubt that forms the living context. This action is the minimization of surprisal. This is Friston's free energy principle enacted in the cell. And from that comes inference as subjective predictions. And this explains why we have multicellularity. It's the major propulsion for multicellularity, why it is a ubiquitous aspect of the living frame, is because organisms must seek to increase the validity of their information in every single separate exclusive information processing unit in the living frame is uncertain. From this, we get one additional characteristic of self-referential information, and these are informational discontinuities. One of them is based on the concept by Scott Forshaw of the third state. And what he talked about, and I think it's a very good idea, is that in order for us to understand things, the distances between the aliquots of information are nearly as important as the informational concept itself. For example, if I took away all the distances between everything I'm written here, including the spaces between the words, it would become much harder for us to interpret it. So that the spaces are really important. The distances between informational inputs are extremely important in the living frame, and computers have no specific sense of that in the same way. It's not meaningful in the same way, just as we appreciate music as the spaces between the notes as much as the notes themselves. They're conjoined. We can't separate them. The second aspect of informational discontinuity is something that can only occur in the self-referential frame. And that is an expected event that does not occur. Cells have an architectural feature that is unlike anything that we have designed to date in engineering, and I don't know of any prospect of it. Cells have embedded information fields, and they have a psenomic architecture. The psenome is a concept that began with František Beluška, my wonderful colleague in 2018. He and I put together the first paper on that. We regard the psenome as the aggregate, the totality of a cell's sensory apparatus. All of the sensory aspects of the cell that contribute to reception, analysis, and ultimate deployment of information. In order for a cell to grasp its place in the world, when there's an unlimited amount of information that theoretically could be received by it, there has to be a field of view. There has to be a representation, but there have to be limits to it, because that's what provides the affordances and constraints that a cell must have in order to function efficiently. And to some degree, it's almost thinking of it as like the Star Trek holodeck. It's the platonic space that, Mike, you like to talk about often. It's that connection, which is still not completely understood, but it has to be there in order for a cell to control its flow of information, because the flow of information controls biology. Each individual cell has one, and cells aggregate them in multicellularity into a coordinated shared n-space epicenome. This is multicellularity in action. Cells share information because they know their information is imperfect, and they're exerting the wisdom of crowds. It's as direct a reason as that. And naturally, the psenome, which is substantially located in its biomembranes, is going to have its electrical biofields that Mike has done such elegant and illuminating work on. So the psenome is an architectural feature of cells, which is unlike anything that we know about in machines and computers. And this is the gateway, the sensory gateway to cellular information management. Cells have particular attributes that are unshared by any digital medium. Cells have preferences. We know that empirically. We show that. You can't do medicine without realizing in infections, the infectious disease, patterns of infectious disease, that cells have particular preferences for specific tissues. We can predict which organism is infecting an individual based on those patterns of behavior that we know cells. Cells have preferences. And it is self-referential information supports preferences in several ways. First of all, the cell is measuring its information internally. It's conducting info computation for value. But because cells have preferences, they're supporting a preferential state of flux. There's valence. We talk about cells in terms of homeostasis most of the time. And part of the problem with homeostasis as an idea, as we talk about it, is that it implies equilibrium. And that's not what a cell does. A cell is in a kinetic, dynamic state. It's a preferential state of flux. It's the state you will find the cell in most commonly if you interrogate it as a snapshot. But it's never equilibrium, as we all know. It's flux. And because the cell is measuring information for value, and it's doing that in order to protect a preferred state of flux, it's valence, it's an experience. And in order to sustain those preferences, cells select their tools. And that's the process of cognitive selection which drives biology. The cellular choice of tools drives biology. Because cells have preferences, they have behaviors. And we know that cells have consistent compact palette of behaviors over time. These have been present from the origin of life forward. We date the origin of life from stromatoliths. Those are evidence of colonial life. Colonial life today, the biofilms that make stromatoliths today, are based on a compact set of behaviors consistent over time that we can enumerate. It's collaboration, cooperation, codependence, naturally competition, and in the normal circumstance of respect for self-integrity. This is how cells have formed multicellular units for billions of years. And importantly, these behaviors drive cell-driven niche constructions. They support the preferences drive the niche constructions. All of this through self-referential meaning, which no computer has, and no non-living system has that we know of, leads to problem solving through communication. And that is the essence of the living flow. It's all based on information flows. And it's based on the ambiguity of information that information must flow. So I will offer that I agree in one very important respect with Mike about diverse intelligences and their continuum. I believe that there is a categorical difference, a difference that makes a difference between the living and the non-living state, but I'm not sure we're going to care. The Anthropocene is new, you know, in geologic time. And you know the phrase, this time it's different. You know how dangerous that is, how often we're wrong with that. I'll take a chance. I think this time it's different. I think the fluidity of the diverse intelligences that Mike is doing such a terrific job of elaborating is going to confound us. I can see that happening. I can imagine a robot that is attractive, and that robot, she says to me, "Oh, Bill, I love your theories. I can't hear enough of them. I'd like to hear them all day long, and I've always wanted to be with an old man with a gray mustache who listens to opera all the time. Now, you are, for me, you are terrific. Oh, it checks all my boxes. I'm all in." We've actually attended to that in cinema. This image is from the promo for Ex Machina. It says the plot was a robot, a future robot, is seductive, seduces a man, outsmarts a man, traps a man. She's just more competent than he, and he reaches the point where he cannot relate to her as a robot anymore, as an android. She's a being, and it confuses him. This is not a new idea. Back in 1959, long before I was born, actually. No, actually, 1959, I was 8. There was a Twilight Zone episode. For those of you in the United States, this was a 5 years of weekly shows, I think, and they were very short plays, and they would have a twist at the end. And this one is a man and a woman in a house. The man is actually known to be a criminal. He had committed murder on Earth. He was sentenced to a life alone on an asteroid. The ship's captain that supplied him a few times a year took pity on him, and a few years back brought him a robot, a beautiful woman-looking robot. And at first he was absolutely resistant and didn't even want to take this gift. But over the years, he comes to regard it differently. The ship comes back. The space captain comes out and says to him, "We got to go back. We're not going to supply you any longer. This is the last supply ship. You've been taken off the list. We're going to bring you back to Earth to complete your sentence." And he goes, "Okay, Mary, my companion, and I will go back together." He thinks that's all set. The captain says, well, there's not enough room for the both of you. There's only, the weight restrictions. We can only take one. And he just goes nuts. He can't believe that he's not going to be able to take his loving companion, who he is now fully convinced is human. The space captain, in frustration, pulls out his ray gun and shoots the robot in the face. And now you see revealed her robot parts. The point is, we are going to get so skillful at melding cells and machines and AI that the differences that make a difference that I'm talking about may not matter to the average individual. So in conclusion, I think the cellular living frame has categorical differences from the abiotic realm. I think it's based primarily on the concept of informational ambiguity. I think that the essential element of info-autopoiesis is not appreciated enough, because that means that we self-generate our information, which means we self-generate our representation. We create our own version of the world. Each cell creates its own reality. As cellular beings, we do the same. We create meaning through inference. This entire mechanism is based on architectural features that abiotic states don't share. I'm not sure they can share. These lead to preferences as an internal state and focused behaviors that come from them, which the abiotic realm does not share. And I think that cells as Kantian wholes of competence and self-referential preferences, that's what enacts its being in the world. So to finish, the essence of the living frame is doubt. And because of that, we fundamentally navigate information space differently from the abiotic realm.
Okay, Bill, many thanks. I think we will have time for maybe very few questions. How is your schedule, Michael?
I apologize. I have a hard break in 11 minutes. I have a meeting after.
Okay, so let me say something before a few questions, that somehow you might have expanded, let's say these dynamics or these aspects of intelligence, you have extraordinarily expanded, and Bill has going to an unsolved fundamental problem of biological information that I think it continues to be unsolved. And so we are caught in between the Scylla and Charybdis, and a fast expansion in these new times. That probably is correct to do that fast expansion as you are proposing, Mike. And you, Bill, go to some fundamentals yet unsolved, but I would disagree with several important aspects, but there is no time for me to discuss with you. Maybe we can have some particular change later on. And then please, questions? Some questions? Okay, Jerry?
Yes, a question to both Bill and Michael. Thank you for the very stimulating presentations. I think a lot of what we're have learned or heard today is intimately involved with the way language is scaled as we move from system to system, and the scaling of language along with this corresponding quantitative representations of the scaling become crucial. And in this respect, I am curious about particularly Michael's response to the notion that does he presume a posteriori notion from a Kantian perspective? And is Bill's major point that he is assuming a priori, something about his usage of language in space-time that is the essence of information?
Bill, would you like to go first?
But I'll just answer to the limits of what I know. our language models that we populate AI programs with are filled with our biases, behaviors, and preferences. And so the emulation that we're receiving is the product of our own representation. I think that's where it builds together. Our language is us, and it all comes together in that fluid pathway. It's a flow of information, I believe. It's precisely that which is going to make it extremely difficult to tell the difference.
Can we let Mike do a little talking, because he's got to leave in 5 minutes?
Wait, please, because there are other questions asked. Mark, please.
I'd like to, I mean, thank you, both of you. This is so stimulating. I want to ask about movement, because in both your examples, they are essentially, it seems to me, there's a very strong kinetic element. It makes me think of Gordon Pask, who felt that we were kind of hypnotized by the digital computer. And he felt that kinetic computation was really important. I can see you nodding, Mike, because I can see that's, and Bill, I think, I mean, we've talked so much about this, but I wonder about this idea of information, whether that is not kinetic, and whether Mike's view is more kinetic.
Yeah. I mean, what I can say is this, embodiment is crucial, and analog embodiment is crucial, but not necessarily embodiment in three-dimensional space. So I think this is really important. There are systems and subsystems, certainly of life, but also of other kinds, that are navigating other spaces, not the three-dimensional space where we're used to seeing, people see an organoid or an AI in a server somewhere, and they say, oh, well, this thing isn't embodied, it doesn't engage with the real world. Well, it doesn't engage with your three-dimensional world, maybe, but it's navigating, in the case of the organoid, it's navigating transcriptional space, physiological state space, metabolic space. There are many spaces that are really hard for us as humans to visualize, and doing that perception action cycle and winning and losing and all of these things that life does, critical in these other spaces. So I think that's very important. And the thing about, I mean, I agree completely with almost everything that Bill said in terms of the ambiguity of information is critical. But one of the places where I differ is this, when we say it's a computer, or it's abiotic, or it's binary, or the information is this and that, I don't believe those are facts about I don't think those are facts. What I think those are models or perspectives that we as observers take on the system. And yeah, but if we have a system and we insist that the binary interpretation of what's going on, and this is what the information means, and we insist on that, yes, of course, all you're ever going to have is the kinds of things that we do not associate with life. But my point is, we need to not assume that our frame and our interpretation of what we're looking at, the formal model that we're using to understand Turing machines, that was the point of that last slide. Not even a Turing machine is a Turing machine. None of these things are our models. There are no computers. There are things that we choose to treat as computers, and there are things that really don't offer much except our view of them as computers. But it's never exactly right. And my point is, we're actually very bad at noticing when we're committed to a frame where we think, well, this is all it is, and we're missing a lot here. So it's a little bit of a metaphysical difference, because I don't think there are facts of the matter as to whether something is a computer or is alive or any of that. But the frames you take have very practical consequences. And what I've been trying to show is that if you actually are willing to take other perspectives, you find surprising things. If you're not committed to the idea that I know what this is a computer, and therefore that's all it's ever going to do. So I think it's about finding the optimal perspectives, and there's going to be many on any system.
Okay, please, jury team seat. You want to ask your question, and then afterwards, Eric.
Hello. So I'm very happy to agree with you, the two conference, and this is very interesting because I think the biology is completely shaken by this these two conference. The first is, as you said, Michael, we have not the tools for understanding what is life. And for the moment, I think I came to the same conclusion. So I am very happy to listen to what you said. We have not the tool because we generally use some model and analogy to understand something, some metaphoric, and we have the most, since Descartes, we have the metaphor of machine to understand life. And perhaps now we are in front of the fact that we have nothing to understand life. We have no good analogy. And this poses the question of this anthropomorphic view of life. And we have to find good tools to understand what is life. And the first one is to question what is a function. And function, the concept of function is perhaps a more powerful concept in biology, and in particular in my field, which is the molecular biology and structural biology, where since the first structure, we have this field, which is structure-function relationships. And perhaps we have to define again, or to understand what is a function. And this is the first question that I have. And function and other things also. Yeah. The second is evolution, and it's for William Miller. You said that the basic unit of life is the cell, but cell it's late in the evolution. We started from molecule. Before cell, there were Luca, and there is molecule. So it's probably important to try to understand what happened before cells, and with aggregation, some molecule together, like the ribosome, which is an example of something living before cells.
Do you mind?
Okay. Thank you.
I'll go ahead and keep it brief because I know Mike has to go. With respect to function, a terrific perspective. When it comes to cells, form and function serve problem solving. And the problem to be solved is the ambiguity of information. The validity of information supports living structures. Form and function follow the need to solve problems. So niche constructions, our habitats, our cellular ecologies, everything about us are aggregated niche constructions. And we are cellular solutions to cellular problems. This is an uncommon frame for viewing biology. I would say your point about understanding the origins of life, absolutely, because the origin of life is coterminous with consciousness as far as my colleagues and I are concerned. And that before is essential for us to understand. However, the cell represented some kind of new thing, an instantiation of consciousness within the cell. And from that, biology effectively begins. I don't know why it happened, but I think it's very important to realize that it did happen. It instituted consistent behaviors that go back 3.7 billion years, and we can build a very coherent, robust biological system from that, as opposed to neo-Darwinian random variations. And that's the epicenter of my work.
Okay, please, Eric, your question to Michael. I think you were asking a little bit before.
He's left.
Well, I found the whole thing very fascinating because much of your vocabulary is a little bit different than mine, but there are also many commonalities between multi-agent systems theory or distributed AI and the work that you're doing. Because I've long seen the cell as an agent, and actually also a multi-agent system, the cell itself. And then we have the problem of, you've related, much of what you've said relates to epistemology. Whereas the work that I do and the people in the DAI area, it's not just epistemology, it's also the pragmatics. In other words, the intentional states of the agents.
Mhm.
And there, I think we have to link the two. Right? Like Miller was talking about, we have an epistemological problem. The cell then generates the full information from the incomplete information it gets. But then we have to also consider the intentionality of the cell and of the body, et cetera, et cetera. But there are other questions I have too, but it's a fascinating discussion.
Yeah.
I think the intentionality is really a very important point. It comes down to the question of consciousness that none of us truly understand. If we asked the definition among us all, we'd get every variety. But you know it when you see it, or you impute it. I think intentionality is the fundamental currency of biology. Intentionality expressed through information flows. Consciousness equals sense awareness having a state of preference, despite ambiguities, preferences. And that never gets emphasized in our biological system. Information flows support preferences, they support behaviors. That's where multicellularity arises. So I think the intentionality is intimately associated with the agency, and I don't think they can be separated.
Yeah, but there's a nice logical link between information and intention. I mean, it's actually a logical process, which has been formalized actually by me, but never mind. So
I'll go one step further.
Yeah.
I want to just say that Mike and I agree with something that's very important. You can't understand what's happening if you stick to only the things that we know. And Mike likes to use the term platonic space. You're all familiar with that. I think you have to grant that the potentials and the actuals come together. The information potentials and actuals come together in the living state in a manner that we do not yet completely understand. And my point is that this merging is a gap that we are not even close to bridging. And diverse intelligences are true, seductive. There'll be a superior conjurer's trick. We won't be able to discern the difference ourselves, but there is a difference. It's the knowing state. It's a grasp of being in the world that the Kantian cell can do. And I don't know why it is, but I know it is, and I know it began 3.7 billion years ago.
Still, I think, Bill, that the fundamental problem of cellular cognition or the origins of cellular intelligence is not well addressed yet. I have taken many notes and I could point to several particulars, but I was thinking that maybe an FIS discussion could be organized so that Mike and you could, we could exchange more with more freedom. Because
we certainly agree that cognition, Mike stated perfectly well, cognition goes all the way down. That's the essence.
Excuse me, when you talk about ambiguity, you forget molecular recognition. It is such a universal, ubiquitous phenomenon, and molecular recognition provides you with basic tools to organize either recognition of form, recognition of sequences, to make, like in the case of the ribosome that Judy has worked. I mean, you make variable recognition tools, and then I think the problem of ambiguity is molecularly well addressed. I don't mean that there is an overall relationship with the environment that it is difficult. But in general, I think the cellular signaling system is well provided by particularly the bacterial cell, one component systems, two component systems, three component systems, and they cover different fundamental aspects of the environment. And so how this relates to the advancement of the life cycle, that it is the fundamental problem of the living cell, is not well addressed yet, at least to my modest knowledge. And I would like to discuss this if it is possible in a FIS session. Although unfortunately they contribute not much lately.
Yeah, Pedro, I would think that this would be a very profitable discussion, because it appears to me, in my understanding of particularly of the nature of continuous mathematics and the relationship between electrical field theory and continuous mathematics, in the sense of allowing for the adding of forces together, can be represented in terms of things at the atomic level. And this in turn implies that inversely, the language that is used by Miller and Michael implies then that there will be an inverse relationship at the corresponding level of sensitivity. And so if you want to start your calculation of control mechanisms and these processes at the molecular level, then you have to reduce your scale of language by 23 orders of magnitude to get to description of the intimacy of the forces. And Philip Anderson, the Nobel laureate in physics, said a long time ago, 73 or so, there's a lot of room at the bottom. And I think AI and Miller and Michael ought to look at that room at the bottom, which is at least 23 orders of magnitude linguistically different from that at the level of human communication, of Shannon information theory, etc.
There's also a lot of room at the top, if you look at it from a logical perspective. And I think Miller and Levin both could apply logic that would make their theories a bit more acceptable, I think. Because right now I hear a lot of vocabulary, but I don't really see that there's much more than vocabulary. Okay, there may be an evidence, but the evidence is interpreted by them. I think if you look at it more abstractly as an abstract theory, that's what I think you really need. It's a theoretical foundation. And I don't see that you have it now.
I won't discuss my own work here because that's published and you can look at it if you wish. But I addressed this problem at least 15 years ago in a conceptual level of how the logic is necessary and how this relates to atomic theory. And that it's published work and you can look at it and find it persuasive or non-persuasive. But the point is that at the molecular level, at the atomic level, the fundamental notions of logic are different. And that is the distinction between electrical, a system of logic based on electrical fields, that is Rutherford's atom, versus the point of logic of Shannon information based on discrete distinction between plus and minus.
But at the bottom, there's also quantum mechanics, and that, again, we go to the discrete with the probabilistic.
I'd like to make
Yeah, that's what Philip Anderson was referring to, was that at the bottom. It was quantum mechanics.
Okay.
And beyond quantum mechanics, there is something. Okay, I think that that Terence Deacon was around. I don't know. Terry, are you around? Terry? Oh, maybe he's not listening now. And also, let me see, Michael Schifrin, Dave Griffiths, something to comment. We are going to close. Some final comments. Gordana, do you want to make some final? Excuse me, Terry.
Yeah, I have no questions because I had to come in late, so I did not hear all of it. Just been listening. I'm hoping that this will be posted so that I can listen through the whole thing. Obviously, I have many comments about even the little bit I heard, but I won't go into it now.
Okay. Thank you. Any more comments? Okay, then let's follow the schedule approximately, and let's say goodbye to our amphitryon.
Maybe I can just repeat your wish to have FIS discussion between Mike and Bill. It would be really appreciated. A lot of open questions still.
Oh, yes.
Yeah. Okay, Bill, do you agree?
Oh, I'd love to. Be a privilege.
Okay.
Thank you.
Okay, we will arrange with Mike how can we prepare this session. Okay, greetings to everybody. Thanks for being in the audience.
Thank you for listening.
And we wait for you in the next dialogue of the International Academy of Information Studies. Okay, bye-bye.
Bye.
Good night.
Bye.
Thank you.